First of all, I want to apologize that I'm not there in person, but I'm giving a fairly important talk to DARPA management, and we made the decision it would be better for me to be here to help prepare the presentation. I've pulled together a selection of slides. They're fairly busy. They have a lot of detail to them, but they have been approved for public distribution, and so I can send you copies if you want to send me an email, and also I think the conference will be putting them up on a web page. It's hard for us to get slides approved, and so I'm choosing a set of slides from previously approved presentations. What I'd like to do first, though, before talking about the Cortical processor, is to discuss the Upside program. Now I'm on slide 2. The reason for this is that the Upside program, although not specifically a neuromorphic program, ends up developing a lot of neuromorphic technology, and I thought it would be of interest to this audience to discuss some of that briefly. One of the things that we had hoped to do, all of us who helped put this workshop together and run it over the last few years, is to infuse into it a much more industrial application orientation, so that we're looking at practical utilization of neural-inspired computing. And so Upside really does that. And so I thought what I would do, many of you may not be familiar with the program, is go over it briefly, and then the latter half of my 20 minutes, I'm going to discuss the Cortical processor and that status and where that program is going. So I'm on slide 3. One of the big problems in the DoD, and this is true in commercial settings as well, is a significant limitations in the power available for doing computation. So if you're on an embedded platform, you're very constrained in the kinds of computations you're able to do. And there are a number of DoD platforms that are very imaging based and are highly power constrained. The purpose of Upside then was to take existing applications and redevelop them using more advanced computational models. Many of the models that we end up using are neural in nature, and demonstrate significant improvements in power efficiency. So in this chart, the vertical axis is really talking in terms of using a notion of capturing features in an image as a notion of computation. And it actually shows that we have a fairly significant efficiency ceiling. This is the best we can hope to do with the digital paradigms that we have, even if we're optimizing the architectures to various degrees. The goal of the Upside program then was several orders of magnitude improvement. In the mixed signal portion of the program, what we were hoping to achieve is 1,000x improvement in power efficiency and 100x improvement in performance. And then we also had an emerging devices component, which would provide another 2 orders of magnitude improvement in speed and power efficiency. The way we're doing this, I'm on slide 4 now, is to exploit the physics of the devices. In the example here, the example shows a couple of oscillators which create an associated memory, which then can be used to do feature extraction. And it does, best match associated memories can be shown to do a Bayesian-like, most likely feature extraction. So this particular example doesn't show a neuromorphic model, but some of the performers on the team are using neuromorphic models to accomplish the same functionality. The second insight we had was that we would be able to find a small number of computational abstractions, and those could be used throughout the pipeline. So we didn't get stuck in the situation where you're building an analog chip, a different analog chip for each stage of the pipeline. What we wanted was some universality, and still using primarily analog components to put the pipe together. What's not mentioned on the slide is the fact that we also had a accuracy requirement. So the performers on the program would re-implement an existing application, and in spite of using extensive analog computing, they had to demonstrate they lost no accuracy in their redeployed application. And in fact, in many of the cases, they actually will be gaining accuracy. I'm on the next slide, slide 5. I don't have time to go through all the various performers. We have 4 main teams, but I thought I would at least show quickly one of the performers. Some of you may be familiar with the Argus system. It is a 1.8 gigapixel sensor flies in a pod. It does what's called wide area motion imaging, or WAMI, and it basically the data are processed through a number of stages. So there's non-uniform compensation, there's debayering, there's feature extraction, target tracking. There's a variety of probabilistic techniques that are used to do that, and ultimately classification of the targets. The goal would be to track 10,000 or more targets. What we find today is that Argus is very platform limited. It can only track roughly about 100 targets or moving elements. The current pipeline has a roughly 3.5 kilowatt power requirement, and with the upside technology, the projection is that they will meet the roughly 100 times faster and 1,000x power efficiency improvement, allowing them to process 40 gigapixels per second, and this is through the entire pipeline, and then also doing it at 5 watts. So this is an example of what's possible with neuromorphic light computation using analog computing. Another part of this program is also memristor work. There's a group at University of California at Santa Barbara and at SUNY in Stony Brook that are developing memristor technology. Some of you may be familiar with Dmitry Strukov, and they're getting some very interesting results using a memristor to do neuromorphic like computation. Next slide, I'm on slide 6. Another one of our performers is University of Michigan, and they're working with Gar Kenyon, who I think may be in the audience there. Gar's developing an algorithm very similar to the one that Bruno developed called locally competitive algorithm, and using that to do various kinds of imaging. Next slide, slide 7. The group at Michigan, Zheng Zhang and Michael Flynn, developed a digital spiking neural net chip for implementing LCA, and are moving to a hybrid chip, which does spiking but does fundamentally analog computation. And they're looking also at achieving the 1,000x and 100x requirements of the upside program. Next slide, slide 8. Also at Michigan, Wei Lu has been developing memristor technologies for a number of years and has some very nice results in using them to do neuromorphic computation. Next slide, slide 9. Another one of our main performers is HRL, and they have a complex pipeline very similar to the BA systems, and they're building a number of custom chips. Again, these are not necessarily neural, but are very compatible with neural-like ideas, and again, leveraging primarily analog computing. What I put up here is just 2 of the devices. So we do have, in addition to the memristors, we have some devices that are being developed by the HRL program, also for doing various kinds of best match association and pattern recognition. And these devices actually operate as oscillators, and coupled oscillators creating these neuromorphic kinds of computation. Next slide, on slide 10. The last performer on our team is the University of Tennessee at Knoxville. And Jeremy Hallman is the primary chip designer there, working with the PI, Itamar Arel, and also working with Silvio Savarese at Stanford on building an imaging pipeline. And one of the segments of the pipeline uses this deep learning chip architecture. The weights it's entirely analog. The weights are implemented, stored in floating gate technology, and they're getting extremely good power efficiency, as are the other performers in the upside program. So I'd like to shift gears now. So I'm on slide 11. The reason I went to the upside, as I mentioned, was to give you a sense that there's analog technology. Some of it directly comes out of neuromorphic computing. Some of it is using neuromorphic-like elements and achieving some significant objectives. And upside is programs, it's a 4.5 year program. It's about 2.5 years in, so there's roughly a year to go, year and a half to go. And we'll start seeing complete test beds using chips are being built now. They're starting to put them into test beds, and we'll be able to demonstrate functionality for all 4 of the pipelines in early 2017. The next question is where do I go next with this? If you look at a sensor data processing pipeline, and this is sort of a cartoon, real pipelines tend to be far more complex than this. And some of you have seen, I've shown this graph many times before, but the front end, we know the algorithms. We're able to build highly optimized silicon to do some of these algorithms. As we move back into the system, we start trying to make much more complex decisions. We're extracting ever more complex data from the sensor data that's flowing through the pipeline, and then we start running into other problems. We don't have good algorithms for the kind of things we're doing at the back end, but also we still have significant speed problems. The Argus system, if it's tracking 1,000 objects or 10,000 objects, then what? There isn't a human can't really intervene in that data stream and try to figure out which objects are the most important to look at more closely. And so there needs to be another couple of stages on these sensor data processing pipelines that bring this knowledge-based component to the pipeline. And that then is the goal of the Cortical processor program. In addition to sensor data processing, if you go to the next slide, slide 12, in my mind, there's a lot of problems in DoD systems that could also leverage the ability to train systems on their workloads rather than actually writing error-prone and difficult to debug and difficult to append and change microcode. So in addition to looking at machine learning to help analyze data, also looking at machine learning to eventually build much more complex systems. To this end, I'm on slide 13, DARPA has put together a fairly complex and comprehensive cortical processor study. I mentioned it briefly at the NICE conference last year. The studies are now in process. They're roughly about halfway through, and some of them are a little more than halfway, and then there are others that started later, so we have some that are only maybe 3 months into their efforts. The purpose of this study was to investigate the algorithm space and to understand if there's opportunity for DARPA to invest in new kinds of algorithms that maybe allow us to move beyond having huge training data sets and going to smaller training data sets, being able to train in real time and have a system adapt in real time rather than using offline training, being able to use unsupervised, make much more extensive use of unsupervised training, or what some people call weakly supervised, where you maybe have occasional labels but not fully labeled training data. Being able to handle temporal data more efficiently, and then finally learning to perform inference to capture and then perform inference over complex structure in data. So we have a number of studies that are strictly algorithm. There's no hardware analysis in this study. And trying to understand some of these, the goal is to determine whether there are biologically inspired features that could be added to the existing machine learning to create hybrid algorithms that might be able to address some of these issues. The program is focused, although I mentioned earlier the ability to do control and adaptive system, the program is primarily focused on imaging, partly because that's a very important space for the DoD and partly because these are really hard problems. So I can't give you any of the results today, but mainly I wanted to let you know that the program, the process studies are ongoing and running. Whether there will be a workshop or not at the end to present results, I don't know yet. One of the things that I also wanted to mention in the presentation is that my time at DARPA ends, and I'm actually leave DARPA next week and move back to Portland State University. We have hired an individual. We have recruited an individual who is going through a security check, who will then hopefully come in and pick up the cortical processor and see it through to a complete program. The next couple slides, 14 and 15, I'm not going to go into these at all. The purpose of these slides were to present to DARPA examples of computational techniques that come from biology and to give a sense of how they could be used in real systems. The cortical processor studies that we have, many of them are using some of these, very few are using all of these techniques, but they together, I think, are promising and provide some insight into where we might go with machine learning algorithms. So that's slide 14 and 15. Slide 16 then is just going back to the notion of structure and data. I believe that probably the most important thing that these algorithms can do for us is to provide a way where we can capture complex structure, exists in the data, and then do inference over that structure. So, for example, in the photo on the upper right side is an Argus picture. It's drawn some tracks, and the notion there is that besides understanding the tracks, you start to see scenarios. You see tracks that coordinate with each other, tracks that are involved in larger scenarios, and the ability to recognize those is beyond our capability today, but it's the kind of things that we'd like to see the cortical processor be able to do. Next slide, slide 17. And to that end, one of the cortical processor studies we're doing is working with Fei-Fei Li to capture complex structure, and in her case, to actually do storytelling over the structure that she's captured in images. Next slide, slide 18. Although the studies don't actually involve any hardware, we do feel that the cortical processor program will have a significant hardware component. Just as GPUs have gone a long way to enabling the deep learning space and the algorithms in that space, so we believe that specialized processors that are optimized to these algorithms can also have a significant impact on the viability and the actual adoption of cortical-like algorithms. These algorithms are very different from the algorithms we do today. Among other things, they're sparse. They're sparsely connected. They're sparsely activated. They use sparse distributed data representations. That changes the connection significantly. They do low precision, typically 1-bit precision, maybe a few bits precision. They compute low precision. Sometimes they're spiking models, sometimes not. I think the jury is out on whether spiking models themselves provide more capabilities to the algorithm, but I do believe that spiking models do provide some significant optimization at the hardware level in terms of needing only to activate a connection when a spike arrives and only having to compute updates to a neuron state when spikes arrive, and could provide significant power saving. We've seen some of that in the True North chip that IBM has developed and is now getting applications ported to. So that is my last slide. Once again, I apologize for a very dense and fast set of slides, and also that I can't be there with you. I would very much like to have participated more directly in the conference. So with that, I think I'll take any questions. I think it's going to be hard to do questions this way, but I'm more than willing to give it a shot.
So are there any questions that I can relay? Or?